Okay, so the chemical reactions that we have kind of been talking about and preparing for are called metathesis reaction or double replacement reactions. These reactions follow this pattern where we have AB and CD representing ionic compounds that are dissolved in water. So what do we call a compound when, or what little subscript do we put on there to show that it's dissolved in water?
Aqueous.
Very good. So A, B, and CD are ionic compounds that are aqueous, and they trade partners to form AD and CB. Notice that A and C still have to be in front because those are what? What is A in, if this is an ionic compound, A and B represent what?
The ions.
That's right. And so what do A and C represent in terms of the kinds of ions?
Oh, cations?
Yeah, cations. Because they're first, the metal ions, or the ammonium ion if it's a polyatomic ion, or if it's an acid, the hydrogen ion, right? Hydrogen ion. So A and C are our cations, and B and D are our anions, and B and D just trade places with the cations, okay? So the charges don't change, right? That is not this kind of a reaction. Reactions where charges change will be couple chapters from now, but a metathesis reaction is where our partners don't change, or sorry, our charges don't change. Now, a reaction doesn't just occur simply because you mix two ionic compounds in solution, all right? So, for example, if I look at sodium chloride combining with potassium bromide, and let's say both of these are aqueous, all right, dissolved in water. Can you tell me what my products would be based on our ABCD model?
The sodium would go with the bromide, so sodium bromide.
Very good. And what else?
Potassium chloride.
Very good. Okay. So this is an example of a chemical reaction. We say, well, it is not actually a chemical reaction. And the way you can tell is because the products are soluble in water. Now, how can we tell if a compound is soluble?
Look at the solubility rules.
That's right. Looking at the solubility rules, all of those compounds, reactants and products, are soluble in water. They ionize. Therefore, if you were to write the ionic equation, remember how we take our our compounds that are aqueous, that are soluble, and write them as ions, because that's what's actually occurring when they're dissolved in water, right? Whoops, plus Br minus. Products, what would the products for this reaction be?
The sodium ion and the bromide ion.
Very good, sodium ion and the bromide ion.
And then the potassium ion and the chloride ion.
Very good. Okay, now none of these are solid. Therefore, they just have to be written as ions. And now if you look at this reaction, and because it's not a reaction, because everything is a spectator. See how nothing has changed. And so the net ionic equation, there is nothing. So you can tell whether a reaction will occur if there's something left when you get to a net ionic equation. Okay? So, reasons that will result in some sort of net ionic equation are, one, if a precipitate forms. So in this first equation here, you have barium sulfate, which is, if you look at your periodic or your solubility rules, it's insoluble. Therefore, a precipitate forms, a net ionic equation exists, therefore a reaction occurs. In an acid and base reaction, acid-base reaction, or a neutralization reaction, you have acids combining with bases and water is formed. Water is not a soluble ionic compound. It won't break up into its ions, right? Sometimes a weak electrolyte, like a weak acid, will form, all right? And sometimes you get a gas forming. Now, if a gas forms in solution, it doesn't stay in solution, or not all of it stays in solution. Some of it rises up as bubbles and leaves. And that prevents the reaction kind of from going backwards. So these are the scenarios that will cause a reaction to occur. A precipitate, water forming, or gas forming, okay? So we now have all the tools necessary to predict metathesis reactions. We can identify the ions that are going to be in reactants, swap their partners, use the solubility rules to see if some of the products are soluble or insoluble, all right? So here's an example of a chemical reaction, HCl, calcium hydroxide, hydrochloric acid, right? We're combining these together. The partners change places. Is this a chemical reaction?
Yeah, because water forms.
That's right. Some kinds of reactions a type of reaction is where water forms. Do you remember what this one's called?
Acid base.
Yeah, very good. Where's the acid?
The HCl, hydrochloric acid.
Very good. Okay. Now, our solubility rules need to be understood well, therefore, because they're going to tell us whether a precipitation reaction is going to occur. So let's look at our solubility rules. Let's have a little review of them. You have yours with you, don't you?
Yeah, I have mine.
All right. So why don't you look at them and tell me if these are soluble or insoluble?
I've been doing my homework, so I'm pretty good at this.
Well, congratulations. That's wonderful. What do you think? Soluble or insoluble?
Rule 2. Oh, I forgot. Can we take a look? Yeah, rule 2 says that everything that has the acetate ion, that C2H3O2 minus, is soluble.
Very good. So calcium acetate is soluble then. Is that what you're saying?
Yeah.
Very good. What about this one?
Carbonates aren't soluble. There's some exceptions. Can I look at the rules again?
Let me bring them up here for you. Whoops.
Carbonate. Yeah, it's not one of the exceptions. So no, that is not going to be soluble.
Okay, very good. How about silver chloride?
Chlorides are, but I think there's some exceptions. I can't remember what they are. Can you bring it up? There's the yeah, see, silver is an exception. So rule 3, the chlorides are generally soluble, but silver is an exception. So silver chloride is not soluble.
Okay, very good. Okay, now let's predict the products of this reaction here and see if we can identify whether an actual reaction occurs between these reactants. Okay, so what are our products going to be?
PB, that's lead, right?
Yeah, lead and nitrate, calcium and hydroxide.
So lead hydroxide and calcium nitrate.
Okay, very good. Can you tell me the formula for lead hydroxide?
PbOH.
All right, it's not quite correct.
Oh, yeah. Let me see. What's the charge on the lead ion? I don't know. Can you tell me what the charge is?
I could tell you what the charge is, but what is the way that you can figure out what the charge is?
Well, can I look at the periodic table?
Sure, I'll bring up the periodic table. You're looking for where lead is?
Yeah.
It's down here. So it's not a transition metal, but it is a post-transition metal. Therefore, it still can have multiple charge states. Only our first 2 rows really have fixed charge states. There's some exceptions amongst here, but yeah, so the periodic table only helps us with those first 2 rows.
Oh, I can just look at the polyatomic ion chart. Let me look. Yeah, the nitrate is -1, so it's lead 2 nitrate. Okay, so it's going to be PbOH2.
Very good. And calcium.
That's a +2 charge, so it's CaNO3 2.
Very good. Lead hydroxide. Oops, I gave away the hard part.
Oh, yeah, it says it's insoluble, the lead hydroxide, because it has the S there.
Yeah, that's right. Now, how are we supposed to figure that out?
The solubility rules. And I have mine here. The 5th one says that, or the 6th one says that, no, the 5th one says that hydroxides are generally insoluble.
That's right. And lead is not one of the exceptions. Okay, very good. Okay, products. What are the products going to be?
NaCl and BaCO3.
Very good. Now you have to make sure that you recognize that the numbers of the ions on the left and the right have to be the same.
Oh yeah, we're gonna have 2 NaCls.
Good. 2 NaCls. Oh, before I show you the answer though, let's predict if there's going to be an insoluble compound. Okay, so let's bring up our solubility rules here. Okay.
Yeah, barium carbonate is going to be insoluble. Carbonates are generally insoluble, rule 6.
Okay, very good. So we're going to hit barium carbonate and sodium chloride. So this is also a reaction because it's a precipitate reaction, right? Okay, here's another one.
So we're going to get sodium nitrate and mercury phosphate. And I can see on the solubility rules, phosphates are insoluble and, well, generally insoluble. And mercury is not an exception. So mercury phosphate is going to be our solid.
Very good. Excellent. Okay, now looking at this compound here, or this reaction here.
We're going to get sodium nitrate and calcium chloride. And let me look at the solubility rules.
All right, while Fred's looking, make sure everybody is looking at the solubility rules yourself and try to determine what the answers are. Don't push pause until you get your answer, okay? All right, Fred, they're back. They got their answer. What'd you get?
Neither of these are insoluble.
Neither the products?
Yeah.
Okay, so what do we say?
Okay, I see. We say it's not a reaction.
That's right. No reaction occurs. Okay, very good. Here's one for you folks at home as well. Push pause, take a look, try to find out what the products are, and see if any of them is going to be solid. Ready? Okay, tell us, Fred.
Well, we got calcium carbonate and sodium nitrate. Sodiums are never precipitates, right?
That's right. What about carbonates?
Generally, they're precipitates. So I think, yeah, calcium for sure. So A.
Okay, very good. A is our solid that's going to result from these reactants combining together. Okay, good job. We'll see you next time.
Okay, bye.